All right, Chemistry 3111. This is a review of the carbohydrates chapter, chapter 24, and I thought we'd start with this one here. It says, draw the open chain form of this sugar. So we have the six-membered ring in a chair conformation, and so if we want to draw the open chain form, I think the first thing we would want to do is number these carbons 1, 2, 3, 4, 5, 6, because we know that in our Fisher projection, our open chain form, we're going to have carbon number 1, which is the carbonyl carbon in the aldose. And then we're going to have 6 carbons total. So if we number them, it goes like this: 1, 2, 3, 4, 5, 6. And we know that anything that's on this side of the sugar is pointing down in our chair, and anything on this side is pointing up. So if we go to carbon 1, you see that we have the beta anomer here, but remember that chiral center isn't manifested in the Fisher projection, so we don't have to worry about that. But if we go to carbon number 2, we see the hydroxyl is down in equatorial, so the hydroxyl would be on this side. That means we have a hydrogen on the other side. We have the hydroxyl pointing down on carbon number 3. Of course, the proton is pointing up, it's left out. But if the hydroxyl is pointing down, that means it's on the right-hand side. Same thing with number 4, it's pointing down and equatorial. And remember that number 5, since we're dealing with a D sugar, that we have the hydroxyl on the right-hand side. So we have all 4 hydroxyls on the right-hand side. And again, let me remind you that the reason this one is on the right-hand side, because this is a D sugar. And so if we go to the family of aldoses and ketoses, and I posted that, the first thing in the chat that I posted today. If you don't see it, it's up there. It says chapter 24, aldoses and ketoses. I don't expect you to memorize the name of all the aldoses and ketoses, but if you look in the chart, you'll see that this one is D-allose. So we have D-allose there. All right. All right, I thought we would try 24.13. So this is question 24.13. It says, provide a name for the compound, provide a name. And of course, you would need the family of aldoses and ketoses, but they give us a nice Haworth projection. So I'll scribble that down here quickly, as neatly as possible. So we have our methylene here. Let's see, we've got the hydroxyl pointing up. We've got the next one going down. We've got the next one going up, and then we have this one going up. Now again, in the family of aldoses and ketoses, which I will provide any sugars that you need, they're not going to be written in a Haworth projection, are they? They're given as Fisher projections. So we're going to make a Fisher projection so we can compare it to the list of aldoses and ketoses. So there we go. Let's number our carbons. We have carbon 1, 2, 3, 4, 5, 6. Carbons 1, 2, 3, 4, 5, 6. Remember that anything that's pointing down is going to be on the right-hand side. Anything that's pointing up will be on the left-hand side. The anomeric carbon, the hydroxyl is pointing up, which is the beta position. But we don't have to concern ourselves with that because, again, that chiral center is not manifested in the Fisher projection. But on carbon number 2, the hydroxyl is pointing down, and so it's going to be on the right-hand side. The next one, on carbon number 3, the hydroxyl is pointing up, so that would be on the left-hand side. Carbon number 4, the hydroxyl is pointing up, that's on the left-hand side. And since this is a D sugar, we're only dealing in D sugars, the last hydroxyl on carbon 5 will be pointing to the right. And so we fill in our hydrogens. And then if you look at the family of aldoses and ketoses, you'll see that this is D-galactose. D-galactose. And so this molecule here, since the hydroxyl and the anomeric carbon is pointing up, this must be beta D-galactose, right? We can add that Greek letter to something that's in a chair or a Haworth projection, right? Because we can examine the anomeric carbon and determine which way it is pointing. I wanted to try question 24.23. Just let me find it in my book here. I wanted to try the first one at least. So this is question 24.23. Again, straight out of our textbook, it says, draw the product obtained when each of the following compounds is treated with acetic anhydride in the presence of pyridine. So in A, we have alpha D, Galacto, Pyranose, and we're treating this with acetic anhydride in the presence of pyridine, and we want to draw the product. Well, the first thing we need to do is we need to draw alpha D galactopyranose. And if we go back here to this problem, we see that we have beta D galactose, and this is a pyranose because we have the 6-membered ring with the oxygen in it. And so we can kind of borrow some of that information. I'm going to draw it as a chair this time just for fun. But if we draw alpha D galactopyranose, here's my pyran ring. The hydroxyl is pointing up because, sorry, the hydroxyl is pointing down because it's alpha. Oops. The next one on carbon 2, the hydroxyl is pointing down, so it's going to be down and equatorial. On carbon 3, it's pointing up. It's going to be up and equatorial. On carbon 4, it's also pointing up. It'll be up and axial. And then we have our CH2OH. Okay, so now we have the structure of the molecule. We're going to treat this with acetic anhydride and pyridine. So I'm going to draw the full structure of pyridine out here. And what that does is that's going to acetylate each one of the oxygens, both the primary oxygen and the 4 secondary oxygens. So let's redraw the molecule best we can. So practice, good practice drawing our chairs. So we have our acetyl group on here. We have another one here. We have another one here. We have one on here. And then we have one on the primary alcohol as well. Remember that when you have OAC, that's the same thing as O with a methyl ketone on it, right? That's an acetyl group. So it's an ester. You're converting it into an ester. Another reaction that we looked at is, you know, if you were to take this same compound, this isn't part of the question, so I'll use a different color ink here, but if you were to take this and treat it with excess methyl iodide, so excess methyl iodide, it's like you do a bunch of Williamson ether syntheses in silver oxide, which is a more mild base than sodium hydroxide or potassium hydroxide, and we looked at why you can't use those bases with a carbohydrate, so you could get some more practice drawing your chair here. And all this would do is it would add a methyl, right? You convert it from a reducing sugar to a non-reducing sugar, and you end up forming a glycoside. And if you don't remember what a glycoside is, well, that's when you have an acetal instead of a hemiacetal, right? Because here in this sugar, we have a hemiacetal, but now in here we have an acetal. And so this would be a non-reducing sugar. Anyhow, just a little bit of practice there. 24.25. 24.25. It says when alpha D galactopyranose is treated in ethanol. So this is question, I'm reading question 24.25. It says when alpha D galactopyranose is treated with ethanol in the presence of an acid catalyst, such as HCl, a mixture of 2 products is formed. Draw both products and account a mechanism for their formation. So let's start by drawing alpha D galactopyranose. So alpha D galactopyranose or pyranose. Okay, we've drawn that enough times today that I think I can draw it from memory. So everything is going to be equatorial except for the alpha, which is going down. And then at carbon 4, this hydroxyl is pointing up too. So those are, but this one is equatorial and this one is equatorial. Again, I just drew that from memory, but we've looked at this molecule a couple of times already today. So there we go. There's our alpha D galactopyranose. So what we're doing is we're treating it with HCl and ethanol. So we're taking it and we're treating it with HCl, okay, in ethanol. So ethanol. So what's going to happen is we're going to convert the primary hydroxyl, which is the most exposed, to a good leaving group. So we're going to do a proton transfer first, like this. And then we're going to end up with something. Let me do a copy paste here to save a little bit of time. copy. There we go. All right, so we're going to end up protonating that. So there we go. I guess I need to erase one of those lone pairs. There we go. So now it's protonated, and now we've created a good leaving group. So we're going to lose that leaving group, and we're going to end up with this intermediate. So let me just draw the intermediate that would be formed after we lose water. So this is loss of water. And then we're going to end up with this guy. So I'll just keep editing this. It's probably the easiest way to do it. So we're going to end up with this molecule here, where we have a positive charge there. And of course, there's a resonance structure where we could draw the carbocation as well. I'm not going to do that right now. But then it says we are in ethanol, and it says we end up with two products. Well, it depends, because if you have the ethanol, so we'll say ethanol, okay, if it attacks from the top face of the molecule, like this, maybe I should use a different color. So it can attack from the top face like this, and then that's going to give us this compound. So we're going to end up with the ethyl ester here. So I'll draw that. And of course, there's an oxonium produced, but of course, there's going to be a proton transfer at the end. We can put this in, and then after the proton transfer, you end up with, you know what, let me just skip that step in the interest of time. So we'll just write proton transfer, and then this would be our final product. But then if you had the ethanol attacking from the underside of the molecule, so if your ethanol, and I know it's not proper to draw two curved arrows on the same intermediate, so yeah, maybe I'll just copy it. Let's see, so we'll do this. There we go. So copy. We'll paste this here. There we go. And then we can just delete the arrow. All right. So if the ethanol was to attack the bottom face of the molecule like this, and I forgot a curved arrow up here, didn't I? There we go. Because we have to have two lone pairs on there. Then after the proton transfer, we would end up with this compound, where we have the ethyl, or the ethoxy group rather, in the alpha position. So let's draw that out. Oops. It's galactose. So there we go. So we end up with a mixture of alpha and beta anomers is the answer. Okay. So we end up with the beta anomer, and we end up with the alpha anomer. And there's a mechanism for both of their formations. So first we do a proton transfer. We have a loss of leaving group. We form the positively charged intermediate, and then I show the attack of the ethanol from either the bottom face of the molecule to make the alpha anomer, or from the top face of the molecule to make the beta anomer. So there you have it. All right, question 24.27 I think is a good question. It just says draw and name the structure of the aldohexose that is epimeric with D-glucose. So this is 24.27. 24.27. So we're just going to start by drawing out D-glucose. And I'm sure many of you have that memorized by so many times practicing. So here's the structure of D-glucose. One of the few sugars I've memorized. So this is D-glucose. And we want to draw the compound that is the epimer at C2. So epimer at C2. Well, what's an epimer? It's a diastereomer that differs in the configuration of only one carbon. So all we have to do is start with the D-glucose. I'm just going to do a little copy paste here. So I'll move it over here. There we go. And carbon 2 is this carbon here. So all I'm going to do is swap the stereochemistry there. So I'm going to switch out, move my hydroxyl to the other side and put my proton over here. So there's my epimer. And if you look at the list of aldoses and ketoses, you'll see that this is D-mannose. So D-mannose. In B, it asks us to draw the C3 epimer. So at C3, so we do the same thing. So we'll just paste the molecule in. C3 is this carbon. So all we have to do is erase this. And this is a molecule that we saw already today, isn't it? Right, this is D-allose. D-allose, where everything is on the right-hand side. So there you go. Just epimer, and again, an epimer is just a diastereomer in which the configuration is switched at one carbon, just one carbon. Next question I wanted to try is 24.28. So 24.28. It's a funny question. It says, if you take D-ultrose or if you take D-talose, okay, and it says if you treat them with sodium borohydride, you end up with the same product. Explain why. So first, let's draw the structure of D-ultrose. So this is an aldohexose. There we go. So let's, oops, can do better than that. So let's pencil in this one. Got our hydrogen here. And then I'll just copy and paste that and edit it. So let's move this over here. So that's D-ultrose. And again, I just got this from the family of ketoses and hexoses. I don't have all these memorized. I'll scribble that off. There we go. And on this side, we've got our we've got a proton. There we go. And then we just round this out. Okay, so these are both aldohexoses. Both are aldohexoses. And then we're going to treat both of them with sodium borohydride in the presence of water. So both of them are going to be NaBH4 in the presence of water. Sodium borohydride in water. And we end up with the same thing both times. Well, why would that be? Because what happens is we're going to reduce the carbonyl function of the aldehyde to a alcohol. So we're going to end up with an alditol. So we're ending up with an alditol. And let's draw what that alditol is. So I'm going to just do the reduction of D-ultrose and just imagine what I'd get from that. So I'm going to paste that in here. And I'm going to convert this into an alcohol. So let's see here, CH2OH. Well, does that make sense? Absolutely it does. Right? If you reduce both of these, you're only going to end up with this compound, because if you rotate it around this axis, right, if you were to spin it 180 degrees this way, you end up with the same molecule no matter what. Okay? So you end up with the product of the reduction of D-ultrose or D-talose. Give me a thumbs up if you follow me on that one. That's just kind of looking at the molecule and realizing that you can spin it around like this, or you can spin it around like this, but you can't flip it like a pancake, because, you know, these bonds that are horizontal are coming towards you. Thanks, Courtney. And the ones that are vertical are going behind the page. Okay, cool. This one I think we did already. Just looking at all the problems I tried here. Let's try 28.32. Let's try 28.32. It says, draw and name the product obtained when each of the following compounds is treated with aqueous bromine at a pH of 6. So this is, let's just try one. So this is 24.32. And we're going to do A. So it says, what does it say? When each of the following compounds is treated with aqueous bromine at a pH of 6. Find the right question. Okay, so we're starting it with galactose. So it says we're starting it with alpha D galactose. Okay, and then we're going to treat this with bromine and water at a pH of 6. So first thing we'll do is we'll draw alpha D galactose. And again, that's one of those compounds that we drew today. We'll start by drawing the Pyranose form. So it's alpha, so this hydroxyl is pointing down. This one never changes. This one is equatorial. This one is equatorial. This one is axial. But we know that that has an open chain form, doesn't it? Right? The open chain form is going to look like this. So we have our aldehyde. And this is what's going to get oxidized, right? Is the open chain form. We have this hydroxyl here. On carbon number 2, it's pointing down, so it's over here. On carbon number 3, it's pointing up. And on carbon 4, it's pointing up. So here's our Fischer projection of D-galactose. And again, we're treating this with bromine in water at a pH equal to 6. So what we're going to do is we're going to oxidize the aldehyde to a carboxylic acid. So we're going to oxidize it to an aldonic acid. So let's do that. I'm going to convert that into, and I'll just use my copy paste here again. Here we go. Copy. Come on, you. There we go. And here's our aldonic acid. So we'll just put our carbonyl. Here we go. There, we made an aldonic acid. All right, let's try 24.34. That's another one I wanted to take a look at with you. So this is 24.34. It says draw and name the pair of epimers that are formed when the following aldopentoses undergo a Killiani-Fischer chain lengthening process. So we're just given this aldopentose. So we've only got 3 chiral centers in the molecule. All the hydroxyls are on the same side. What are the conditions for the Killiani-Fischer synthesis? First, we're going to treat the molecule with HCN, and then we're going to treat it with hydrogen and barium sulfate. There we go. So we end up lengthening it, right? So we've got a total of 1, 2, 3, 4, 5 carbons, but carbons 2, 3, and 4 are going to be the bottom carbons in this structure, right? If I have 2, 3, 4 like this, all 3 of those are going to maintain their stereochemical configuration. And then I'm going to add 1 stereocenter to it like this, and then I have my aldehyde on the top like this. So what are the structures going to look like? Well, let's keep the skeleton here, and we'll put it down twice. So I'll just move this over a little bit. And same thing with this guy. Move it over. So what are the epimers? I'm going to have the hydroxyl on the right-hand side on one, and I'm going to have it on the left-hand side of the other, like this. So this one is D-allose, and this one over here is D-altrose, Let's see here. Let's try one last one, just for fun. This is 24.38. It's kind of a funny question, but I think it's worth taking a quick peek at it. It's 24.38. Luckily in the iPad I have the copy paste tool. So it says when D-glucose undergoes a vol degradation followed by Killiani-Fischer chain lengthening process, a mixture of 2 epimeric products is obtained. Identify both epimers. I'm sure that a lot of you can just figure this out in your head and that you don't need to write it down. And that's cool. There's nothing wrong with doing reactions in your noggin. I don't have any problem with that. But I think it's worth taking a quick peek at it. So let's take a look here. We're going to start it with D-glucose. Okay, so here's my D-glucose. Again, I recommend memorizing D-glucose. So the hydroxyl is pointing like this on the right-hand side, and then you just figure out the rest like this. So this is D, glucose. So first we have a vol degradation. So in the vol degradation, in step 1, we treat it with hydroxylamine. Step 2, we treat it with acetic anhydride. And then in the third step, you treat it with sodium methoxide. And that's going to remove a carbon, isn't it? So if we take our original D-glucose molecule, we can literally just copy it and edit it because we're just removing a carbon. So we're going to put this like this. We're going to erase this. We're going to erase all this stuff here. Okay, so we only have the bottom 3 chiral centers. And then we have this molecule here. Oh, I guess I deleted this. All right, so we have this intermediate, and then we're going to subject this to the Killiani-Fischer chain lengthening process, and I'm probably going to run out of space. So I'll write it like this. You're going to treat it with HCN in the first step, and then in the second step, we treat it with hydrogen and palladium, with barium sulfate in water. And what are we going to end up with? So we're going to end up with, we're going to end up with the original molecule, aren't we? We're going to end up with D-glucose again. And then we're also going to end up with the C2 epimer. Because remember, when you do the chain lengthening process, okay, you're going to add a carbon in the stereocenter. It's going to be racemized. So let's take this one. And we're going to flip this over here like this. And there we have it. So we end up with D-glucose. D-glucose. And then we also end up with D-mannose. All right, good practice. And again, this is the Killiani-Fischer. So Killiani-Fischer chain lengthening. And the first one was the vol degradation. So make sure you know these reactions stepping into quiz 24.